Hello learners, in continuation with my previous lecture on state variable analysis, I am continuing with the same and will be discussing about few other concepts of the state variable analysis technique. So I'll be having a brief revision of the definition associated with the state variable. The first is the state. State of a dynamic system is the smallest set of variables such that the knowledge of these variable at any time t equal to t naught together with the knowledge of the input for t greater than equal to t naught completely determines the behavior of the system for any time t greater than equal to 0. Then state vector. State vector is the n state variable that are needed to completely describe the behavior of the given system, and these state variable can be considered as n component of the vector capital X. This vector is called the state vector. Then we are having the state space, the n-dimensional space whose coordinate axis consists of x1, x2 up to xn, where these are the state variable, that is called a state space. So if you want to go into the details of these, you can watch my previous lecture. So we'll be continuing with the determination of the state variable model. So first of all, we'll get the state variable model of an electrical system. So within this diagram, you can see an electrical system that is made up of current source, then a resistor, two inductors, and a capacitor. So whenever we, as a, you can say, key element, as a key feature, that whenever you are constructing the state variable model of the electrical system, it is always better to take up the voltage across the capacitors and current through the inductors as the state variable. So since we are having three basic elements which can be used for the energy storage, so C1, so voltage across this capacitor, then current through the inductor L1 and current through the inductor L2. They are considered to be state variable over here. Although the state variable can be chosen depending upon the user, but this is the basic rule for selecting the state variable model of the electrical system. So here we have decided three state variables, that is the voltage across the voltage across the capacitor, current I1 through the inductor, and current I2 through the inductor. So we are having three state variables such. So first of all, we write down the basic equation of the system. If we reconsider this circuit, we can very well see that L2 into di L2 by dt, that is equal to E1. So it can be rewritten as DIL2 by dt is equal to this. Then at the same time, we can see that IA minus IL2 minus IC1 minus IL1 is equal to 0. And IC1 is what? Current through the capacitor, that is equal to C1 into DE1 by dt. So DE1 by dt, that is the voltage across the capacitor. It can be written as equal to 1 divided by C1 IA minus IL2 minus IL1. Then voltage across the inductor L2 E2, this can be written as equal to L1 into DIL1 by dt. So this is equal to E1 minus RIL1. We have applied the Kirchhoff's voltage law. Then keeping DIL1 by dt on one side, we get the equation of E2 as equal to this. So E2 is simply working as a output. So E2 is the output voltage. We are having three state variable, IL1, IL2. Here we have shown these three state variable, IL1, IL2 and E2. So IL2 dot is equal to E1 by L2. So it means that IL2 dot, this is equal to, this can be represented as E2 divided by L2. So that is represented by first row of matrix A. Then we are having E2 is equal to E1 minus, this is equal to this dE1 by dt. This is equal to, the second state variable is not E2, this is E1. Sorry for this mistake. So instead of E2, read E1 over here. So E1 dot is equal to 1 by C IA minus IL2 minus IL1. So it is minus 1 by C1 into IL2 minus IL1. So these two elements, they are representing the this equation, that is dE1 divided by dt. Then the third equation is in for the DIL1. This is IL, the third state variable. So dl by dt is equal to 1 by L1 E1 minus L. So it is represented over here. So we'll get the matrices A and B as shown over here. Similarly, the output is represented by E2. So this is equal to E1 minus RL1. That will give the matrix C as equal to this. So in this way, we have first of all decided the state variable. Then we have written the basic electrical equations from the electric circuit elements. Then we have applied KVL, KCL, and all the loop equations. And we have got, as we have decided three state variable, please read E1 over here. IL2, that is the current through this inductor. IL1, that is the current through this inductor. And E1, that is the voltage across the capacitor. That's what we had said, that whenever we are having the inductor and capacitors within a circuit, then the current through the inductors and voltage across the capacitors are taken as the state variable that we have chosen. E2, please read E1 over here. Then we have just from these we have derived the equation for IL2 dot, then E1 dot, then IL1 dot, and from there we have developed Q is this. So Q dot is equal to AQ plus BU. So after substituting, we are getting the value of A matrix as equal to this, B vector as equal to this. And since the output voltage is E2, so E2 is equal to E1 minus RL1. By substituting it over here, we are getting the value of the C matrix or the C vector as equal to this. So once we have identified what are the state variable, once we have got the values for the matrices A, B, C, and D, it means our state variable model is complete. Then another thing is that sometimes we have to derive the transfer function from the state variable model. Let us consider that a state variable model is represented as Q dot T is equal to AQT plus BQT. This is the state equation. QT here is representing the state. YT is equal to CQT plus DUT. It is representing the output equation. Now we just take up the Laplace transform of both the equations. So Q dot T, when we take up its Laplace transform, we are getting SQS. This is equal to AQS plus BUS. Similarly, the Laplace transform of this equation gives YS is equal to CQS plus DUS. Then we have just taken BUS on one side within this equation. We keep BUS on one side, all the other quantities on the other side. Then we solve it for QS. Then we are getting the value of QS is equal to SI minus A inverse into B into US. Then SI minus A inverse, this is written as phi S. This is called the state transition matrix, and this is equal to SI minus A inverse. And when we substitute it, YS will be equal to C into QS is equal to what? QS is SI minus phi S into B into US. We just substitute over here. Here we are getting the output. So now we can get the transfer function that is equal to YS divided by US. YS is equal to this. US, when it gets divided by US, we get C into phi S into B. So this is equal to C into SI minus A inverse, because phi S is equal to SI minus A inverse. SI minus A inverse into B plus D. Then for this inverse, we can write down this as adjoint divided by matrix, so that we have substituted and will be able to get the equation for the transfer function. So this is the transfer function. In case D is 0, then transfer function will be simply C into SI minus A inverse into B. So when we are taking the transfer function, then this equation in the denominator of the transfer function, as I have already told in my previous lecture, that this denominator, when equated equal to 0, just gives you the characteristic equation of the system, and it plays a very important role in determining the stability of the system. If roots of all the roots of this characteristic equation are lying in the left half of the S plane, the system is stable. Otherwise, it may be marginally stable or it may be unstable. Then first, that was the conversion from the transfer state space model to the transfer function model. The other conversion can be from the transfer function model to the state space model. So this conversion can be in a number of form. So I'll be discussing two major type of the forms. That is the controllable canonical form first we'll be taking. Let us consider that the transfer function hs is equal to ys divided by us. It is represented like this. Here you can observe that the degree of numerator polynomial is less than the degree of denominator polynomial. This case we have considered the overall process actually becomes difficult when the degree of the numerator becomes equal to or higher than the degree of the denominator. So hs is equal to ys upon us. So it can be represented as equal to this. Then we have taken hs, that is the transfer function, that is equal to ys divided by us. Ys is the output variable transfer Laplace transform. Us is the input variable Laplace transform. Then we equate numerator as both the numerator and both the denominator. So we'll get these equations. Ys is equal to this and us is equal to this. So from here we just multiply and numerator and denominator by zs. So that we'll get, and we take up inverse Laplace transform. So we will get y is equal to b naught s square zs. So it will be b naught z double dot plus b1 z dot plus b2 z. Similarly, u will become equal to this. Again, we choose up the state variable. First state variable is chosen as equal to z, other as equal to z dot, other as equal to third state variable as equal to z double dot. Just consider that whatever is the degree of s, we have to consider the state variable accordingly. Since there are the degree of s is 3, so it means we have to consider 3 state variable. So first state variable directly, second its first derivative, and third its second derivative. Then first of all, the two equations we can get directly. The derivative of the first state variable is equal to the second state variable. Derivative of the second state variable is equal to the third state variable, and the derivative of the third state variable that we can get from the basic equation. So that is equal to minus a1 into this we can get from here. So this is z triple dot. So this is equal to z double dot. So this is equal to u minus a1 z double dot minus a2 z dot minus a3 z. So that we have substituted the value of those. So we are getting q3 dot. So it means that we have got the state variable model q1 dot, q2 dot, q3 dot. So now we just need to form the output. So output is equal to y. So y is equal to b naught z double dot plus b1 z dot plus b2 z. So this is equal to z double dot is q3, z dot is q2, and z is equal to q1 that we have substituted. So now from these equations, we can write down the matrices A, B, C, and D. So q1 dot, q2 dot, q3 dot, they are constituting q dot. So this is equal to q1 dot equal to q2. So first this is equal to q is q1, q2, q3. So this multiplied by q2, so this here will get a 1. Similarly, q2 dot is equal to q3, here will get a 1. Then q3 dot is equal to u minus, so here it comes a 1, minus a3 into q1 minus a2 into q2 minus a1 into q1. So that we have substituted, we have derived the value for A matrix and for the B matrix. And similarly, when we come across the output, output is equal to CQ plus DU. Here we are using the term, in the previous lecture, the state was, I used the variable X to denote the state variable. Here I'm using the variable Q to represent the state of the system. That is up to you. You can give any name to the state variable. Here I've given the name Q. So Y is equal to CQ plus DU. So y is equal to, so q is basically a vector here. That is q1, q2, q3 vertically. So when it gets multiplied by B2, B1 and B0, so we'll get this equation, and it's having zero dependence upon U, so multiplied by U. So A matrix is this, B is this, C is this, and D is this. So, so that was the conversion of the transfer function model to the state space model in the controllable canonical form. So, if we generalize it, you can very well see over here that over the diagonally, we are getting one entry, and over here the coefficients are minus A3, minus A2, minus A1. So here, first of all, we'll write the equation in this way. So instead of making all these derivation, you can directly write down also the state variable model from the transfer function, because in the y we are getting B2, B1, B0. So B2, B1, B0. Just write the transfer function in this way, identify A1, A2, A3, B0, B1, B2, and you can directly write down the matrix A and B. Then matrix B is simply all entries 0 and last is on 1, and matrix D is equal to 0. And this is for the third, this is second order, this is the third order system, and this can be generalized for the nth order system as all entries 1 here. In the B, last entry is 1. In the D, this is equal to B0. And in C, we are having Bn minus An B0, Bn minus 1 minus An minus 1 B0, and so on. And here we are getting the entry as minus An minus 1 minus An minus 2 up to minus An. So you can just put up the transfer function in this form, and you can directly form the state variable model by using these formulas. Then the second type of the representation of the state variable model from the transfer function is observable canonical form. Again, I'm considering the simplest case where the degree of the numerator polynomial is less than that of the denominator polynomial. So in this case, we have just made up a cross multiplication, multiplied this by this and this by this, we are getting this. Then we have just kept s cube ys on one side, all the things on the other side, then we are getting this equation. Then we have just made up the y triple dot is equal to this. Then we have made up the definition of the state variable as q1 is equal to y, q1 dot is equal to y dot. So this will be represented as equal to this. Y dot, it is equal to this. We have represented it in terms of the, because wherever we are getting a single, there will be having a single integral. So b1 into u dt. So, and wherever we are having the double dot, there will be using the double integral. So we have got this equation from this equation, and then we have chosen the state variable as q1 is equal to y, q1 dot is equal to this. Similarly, we can write down the equation of q2 in this form. Then we can get the value of q2 dot. Then we have written the equation of q3 in this form, and then we can write down the value of q3 dot. Once we are having the value of q1 dot, q3, q2 dot, and q3 dot, we can identify q dot, and we can use the equation to get the value of A matrix, B matrix, C matrix, and D matrix. Then further it can be generalized. This is for the third order system. So for the nth order system, it can be minus A1 minus A2 up to minus AN. And all these values will also be B0, B1 up to Bn minus 1. And here we are getting the same. So this is the conversion of the transfer function model to the observable canonical form of the state variable model. So in general, we can, and that was for the third order system. And for nth order system, in case we want to write down the A matrix, we can use this formula from this basically transfer function. B can be written as equal to this, C can be written as equal to this, and D can be written as equal to this. So it means that it is possible to convert the transfer function model to the state variable model directly, and state variable model to the transfer function model directly, and get the benefit of each model wherever required. So we'll be continuing with few other aspects of the state space model, that is because it is used to ascertain the controllability as well as observability of the system. So we'll be discussing into details the use of the state variable model to ascertain the controllability and observability of the system in my next lecture. So thanks a lot for the patience learning. So thank you so much.